And let's begin with this schematic. So this is the microscope column itself. And inside the column there's very high vacuum. And these represent the pole pieces of the objective lens, and we'll talk about them in a minute. And this represents the tube in which the sample is inserted. And I've drawn two circles here to represent a ball valve that seals the column from the outside environment. Most electron microscopes are what we call side entry because the sample is inserted from the side of the column. The other type is top entry, in which a sample would be coming in from the top of the column and placed down into the chamber. Within the side entry microscopes, there are some that you insert the sample manually, and then some of the more sophisticated modern microscopes have automatic sample loaders. And I'm going to show you in this schematic the older class of holders that are manually inserted into the side of the microscope. And as you get started in cryo-EM, almost for sure you'll be practicing and learning on one of these style microscopes. And so you'll be presented with a holder. So here I've drawn the holder, and it goes into a fine tip, and this represents the EM grid at the end. This is the sample. And this holder will have a little pin coming out of the top of it, and these are supposed to represent an O-ring that can create a vacuum seal. And so as you insert this holder into the microscope, the pin will engage a structure inside the insertion tube. There will be a sensor right there, and it will tell the microscope that the sample has been inserted at least until these O-rings can form a seal with the insertion tube. And once there's a seal formed here, then the vacuum pumps will be used to establish a vacuum in this antechamber. Once there's a high vacuum established in this antechamber, the microscope will report that state, usually with a light that changes color, say, that tells you that it's safe now to rotate this ball valve and connect this chamber with the microscope column. So once the light changes, you can then rotate this sample, and as you rotate it, this pin will trigger a mechanism that connects to the ball valve, and the ball valve will rotate, allowing you to insert the sample holder through the center of that ball valve and put it into the microscope column. And the O-ring slides down the insertion tube and maintains the seal. And so sample insertion, first you put the sample into the antechamber, a sensor triggers that the seal has been made, it pumps a vacuum to prepare for connection with the column, then the light changes color, letting you know that it's time to proceed, then you rotate the sample holder, triggering the rotation of the ball valve, and then once the ball valve is rotated, then you can push the sample holder all the way in, depositing the sample into the middle of the microscope column. Now let's look at an enlarged view of the sample chamber within the microscope column. Now, while I've always been drawing an EM lens as a coil like this for schematic purposes, in fact, in electron microscope lenses, these coils are very carefully wrapped in specific patterns, and they're ensheathed with metals that guide the magnetic field lines to produce a better lens. And the metal pieces that guide it are called pole pieces. So in this schematic, these objects, this object, this object, this one, and this one are the pole pieces of the objective lens. And I've drawn circles here and X's here to suggest that a wire goes around through it like this. So these are coils of the objective lens. And of course they're stacked deeply. There's thousands and thousands of coils through there. And when a current has passed through those coils, it creates a magnetic field. As we've talked about before, there's magnetic field lines that are going to do the focusing of the electrons. However, in order to intensify the field lines in just the right place, the coils are wrapped with a metal that entrains the magnetic field lines so that they pass more directly from one pole piece right to the other. And this allows the magnetic field lines to be shaped more carefully and concentrated at just the location where we need it. And so this distance is called the pole piece gap. And the smaller that gap, the more precisely the magnetic field lines can be controlled, and the higher the resolution of the electron microscope. However, we don't want a pole piece gap that's too small, or else it will limit our ability to rotate the sample. Remember, the EM grid is about 3 millimeters across, and we would like to be able to rotate it back and forth within the microscope. And so if the pole piece gap is too small, then we can't rotate our grid. And it's for that reason that cryo-electron microscopes typically have a bigger pole piece gap than your average electron microscope for material sciences. In addition, one of the problems in electron cryomicroscopy is that there is always present in the column some water. And so I'll draw water molecules like this. Of course, it's a high vacuum, but there's always a little bit of water present in the column. And because in cryo-electron microscopy, the sample is held at about 80 Kelvin. Usually this is through thermal contact with liquid nitrogen. In other words, there may be a dewar of liquid nitrogen out here outside the microscope that's in thermal contact with the specimen holder that keeps the grid itself at approximately 80 Kelvin. So because this is a very cold surface, unfortunately, water molecules in the column, if they come and they hit that surface, they'll freeze on it. And so the water comes down and it hits it, and what you see is that as time progresses, your sample becomes contaminated by water vapor freezing onto it. To help mitigate this problem, almost all cryo-electron microscopes have two plates above and below the sample, and these plates are like apertures in that they have a hole in the middle. So there's one above the sample and below the sample, and they're connected. And these are also linked thermally to liquid nitrogen, so that this cryo box is also at approximately 80 Kelvin. And they help protect the sample, because now when water molecules fly towards the sample, most of them will hit the cryo box. Still, some may fly in through the cryo box aperture and still be deposited on the sample, but the probability of that happening is much reduced with the cryo box. But this is another reason why the pole piece gap in an electron cryomicroscope needs to be a little bit larger to house both the cryo box and the possibility of tilting the sample. Now I'm going to draw kind of an oblique view of the electron microscope grid being held by that sample holder. Let's suppose this is the EM grid, and obviously, so we're looking down at it from an angle. And let's suppose one of the targets that we'd like to image is over here, and one of the targets we would like to image is over here. Now, there is a particular optical axis of that objective lens, and the lens will perform best if we leave the beam as nearly as possible coincident with the optical axis of the objective lens. In order to achieve this, the sample holders are built with the possibility of being able to move the grid further in or out, also left or right. And this is done by elements within the specimen holder apparatus that simply push the tip a little bit in one direction or the other. as the tip is suspended by these O-rings and other elements of the specimen holder. Now, in addition to moving left and right, we would also like to be able to rotate the holder and rotate the grid inside the specimen chamber. Now, the sample insertion tube, this tube here, is a fixed entity. It's a fixed tube, but the sample holder itself can rock a little bit up and down, and it can spin within this tube. And so if we consider this tube here, there is a special axis exactly down the middle of this tube through the specimen chamber. And if our sample is exactly on that line, as it rotates, the object of interest will not rise or fall within the column. Instead, it'll stay exactly where it is. This height, this plane within the objective lens, is called the Youthcentric height. And it again is defined by this permanent insertion tube that exists. The center axis of that insertion tube defines the Youthcentric height. And when you insert a sample into the electron microscope, the first thing to do is to try to move it up and down in Z in order to put the object of interest right at that Youthcentric height, so that if you then tilt it, it won't rise further or lower further in the microscope. See, if the Youthcentric height is here, and you insert your sample down here, and then rotate it, what will happen is it will roll and move up and down radically within the column. You don't want that. You want it to stay exactly where it is as it rotates. And that's done by putting it at the Youthcentric height. So in order to achieve this, there's additional motors within and dials within the microscope that allow you to move that tip of the specimen holder up or down within the column so that you can place it at the Youthcentric height. In summary then, the sample insertion tube is a tube that's permanently mounted on the side of the microscope. And within that tube, it has a particular axis. And when we insert a sample, we insert a grid, and there may be a cell or some object of interest on that grid. We first have to move the grid left or right or in or out further within that tube so that the object of interest is directly underneath the optical axis of the objective lens. In addition, we want to move the grid either up or down so that the object of interest is exactly at the Youthcentric height of the tube, so that when we rotate it, it doesn't rise or fall further.